All right, let's talk a little bit more about semi-direct products. And when I first introduced them, if you've ever seen semi-direct products before, you may have been a little perplexed by how we define them, because there is another way that sometimes is the definition that you'll see first of what a semi-direct product is. And in fact, it was the one that I saw first. And so what we're going to do is we're going to go back and talk about one of the other definitions of a semi-direct product, and then kind of relate it to what we did before. And so what we're going to do is we're going to let H and N be subgroups of G, and we're going to let alpha be a group homomorphism from the group H to the automorphism group, so I'll just say aught subgroup of N. So define G to be H cross N as a set. So this is not the direct product of H and N, like it's not the group direct product of H and N, it's the set direct product, i.e. we have G being, the elements of G, we write them H comma N, it's a set, and give G a composition law. And this is going to look a little weird. I want this all to be on the same line so that we can reference it. And let h1 x1 dot h2 x2, we're going to find this as h1 h2, the product here. Of course, the product here is going to be in H. And then here we have alpha of H2 inverse of X1, X times X2, and this times, of course, is in N. Be a law of composition. On G. So let's see here. Remember here, so alpha goes from H to the automorphisms of N. So what you need to do for alpha is you need to, once you plug in an element H here, alpha applied to H2 inverse, this is going to give you a function in the automorphism group on N. And so what we do is, since this is a function on N, we plug in this element x1 of N, and feeding x1 through this automorphism will give us another element of N. And so what this really is it's just this alpha H2 inverse x1, that's all just some element of N, and we're multiplying it by x2, which is another element of N. Let's see here. I claim that G is a group. And when you see this, your heart should sink, because you think, oh, how do we prove that something's a group? We haven't talked about that. Oh, we have to go back and prove that this thing is closed under multiplication, and that it has, well, not really closed under multiplication. We need to prove that it has a, oh, another thing to mention. Okay, so I guess closed under multiplication. So this is actually a composition law on G, because H1 times H2 is, since H and N are subgroups of G, H1, H2 is going to give us an element of H. And like I said, alpha H2 inverse X1 is going to give us an element of N. And X2 is an N, and so this is just a product of two things in N, and so this is an N. And so indeed, this gives us an element of H cross N. Well, I guess it doesn't quite make sense to have these be subgroups of G and that. I think what we actually want to do is let these be groups. Because I don't think we need them to be... I don't think we need them to be subgroups of G, because we don't even have G yet. I think what you can do is you can just start with any two groups, H and N, and any homomorphism, alpha, and define G that way. And yeah. So let's see here. I claim that G is a group. So okay, going back to this, what do we have to prove? We have to prove that we have an identity, we have to prove that we have inverses. But that's not it. There's one thing else that we need to prove that we've kind of taken for granted with every other single example that we've done, and that is associativity. We have to check that this thing is associative, and that is really laborious, but we have to do it. This is the type of problem, the type of computation that I've heard professors say you only do once in your life. We got to do it once to make sure that it actually works, but then after that we just kind of forget about it and just take it for granted. For associativity, h1x1 times h2x2 times h3x3. And of course, looking at this function, this law of composition, you know this is not going to turn out well for us. So we have h1, h2, alpha h2 inverse x1 times x2 here. This all times h3, x3. And then here, this is h1, h2, h3, comma, and then we have alpha of h3 inverse, and then for this thing, we have to plug in all of this, and so we have to plug in here alpha of h2 inverse, x1, x2, this all times x3. Okay, but this is h1, h2, h3, and now we have, did I make any changes in this? So here what I'm going to write is I'm going to write alpha h3 inverse composed with alpha h2 inverse, this all of x1, x1, and then this, oh, I see what I did here, I think. So we're applying alpha h3 inverse to this whole thing, but this is a group homomorphism. So first we can apply alpha h3 inverse to this part, which I will write as alpha h3 inverse composed with alpha h2 inverse of x1, and then we multiply it by alpha h3 inverse of this because this is a homomorphism. We can break it up like that. So this is alpha h3 inverse of x2 and then of course this we're still multiplying by that x3. So this, the h1, h2, h3 stays there, and that's going to just keep sticking around. Now this alpha h3 inverse of alpha h2 inverse, remember these are homomorphisms, you can bring the inverses out front, and inverse times inverse equals flip them and then inverse of the whole thing. And so this happens to be alpha of h2 h3 inverse applied to x1 instead of alpha h3 inverse of alpha h2 inverse. And of course, you can go from the composition to the product again because this is a homomorphism. You know, I think there we might be using, I think in one case we're using that alpha as a homomorphism, and in another case we're using that like alpha H3 and alpha H2 are homomorphisms here, automorphisms. But whatever. You can expand this step out more if you don't quite see the connection from here to here, but trust me, it works. So we have this, and this, of course, we have this times alpha H3 inverse, x2 times x3. Okay, so now we're in business because this is h1 x1 times, and of course this is the part where the way you do these types of checking associativity is that you sort of work backwards. And so this isn't an inequality that you would see going this way. You would start here and then expand it out and get this. But anyways, this works. And then this, of course, is h1 x1 times, and then h2 x2 times h3 x3. And there we go. For identity, or the existence of the identity, we have hx times, now what do we think should be the identity? Well, h cross n is our group, and h and n both have identities. So we're just going to try en and see if that works. So this is going to equal heh, and then alpha inverse of x of en. But alpha inverse, alpha is a homomorphism, so this is going, so alpha of inverse is going to be the same, well, inverse is just and so this is, and because this is a homomorphism, it must send the identity to the identity. So this is just the identity automorphism, so you plug in x and you get x. And so this whole thing is x, and this is en, so that's x. This is just h, so this is h comma x. Okay, so that's what we wanted. H times this is hx times this is hx. But if you, going the other way, you can see that this is this alpha h inverse of en x. Let me just write this out first. hen dot hx. Again, here we would be working backwards. So if you start with the multiplication in this direction, then of course you have the eh times h here, and then you get the alpha of h inverse en times x. And alpha h inverse is going to be a homomorphism, and so it must send the identity to the identity. And so we don't really care what automorphism this is. We know that when we plug in en, we're going to get en out, and so this is just going to be en times x, which is x. So there we go. Now for inverses, this one is a little tricky, and you wouldn't quite think of this on your own necessarily. It would take some work to figure it out. But this is what the inverse looks like. You take h inverse, that's not too hard to figure out. But then here you need alpha h of x inverse. And so let's check that this works. This is h inverse, alpha h x times this thing, which is alpha h x inverse. But this is a homomorphism, so we can bring the inverse outside. And so this times its inverse is just the identity, and so this is going to be en and h inverse alpha h x inverse. Oh, and obviously this is going to be an element of hn because this because h being a group means that h inverse is in there, and this being an automorphism means that plugging in an element of n will give you an element of n. So anyways, this times hx is going to equal h inverse h, comma, alpha of h inverse applied to alpha h of x inverse times x. So then this is equal to h inverse h, and then, so alpha, since alpha is a homomorphism, taking alpha composed with alpha at h composed with alpha of h inverse, so you bring this inverse out here, and so this is going to be alpha of h inverse, and we're composing it with alpha of h, and so we're going to get the identity map here. And so if this is the identity map and we're plugging in x inverse, we're just going to get x inverse, and then the x there stays, and so we have inverses. Versus. So hence, G is a group with this composition law. And also, we write G as H semidirect product with N, but we use an alpha here under the semidirect product. And this is just alluding to the fact that we have this alpha, which is this homomorphism here. And this alpha is what we're using to take the product of H and N, because that's what we use in this formula. So anyways, this is a way, I think this is sometimes called an external semidirect product, because for the other, and the other one I think is called an internal semidirect product, because in the first case what we did is we started with a group G, and we took two subgroups and suppose that they have some nice properties, and then we prove that we can write G as a semidirect product of those two subgroups. Here, we just start with any old groups H. So in that scenario, everything was happening like internally in the group G. Here, like I mentioned before, H and N are just groups by themselves. They can be anything, but we have to have some alpha, some homomorphism here that does this. And then you sort of glue these two things together to get a semidirect product. And so it's sort of like external in the sense that it's not internal. Like it's not occurring inside some outside group. You just happen to find some two groups and some homomorphism you could use to put them together. So anyways, what is the relation between this semidirect product and the semidirect product that we talked about previously? And that's the question that we're going to answer next time.